let's find the directional derivative of f of xy when f of xy equals a cosine inverse of xy. And we're going to find this derivative at the point 1, 0, which means we'll get a numerical value for it. So we're going to find that, and it's going to be in the direction of v equals I plus 5j. So basically, in layman's terms, we want to find, if you think of f of xy as a mountain, and you think of v as a compass direction, we want to know how steep that mountain is in the direction of v. You can think of v as a compass direction, right? If you went right 1 and up a distance of 5, if you looked in that direction, then how steep would the hill or mountain be if you're at the point 1, 0, f of 1, 0 would be the z coordinate, okay? So that's what we're doing. You know, if you've ever gone up a hill, if you hike in one direction, it may be steeper than hiking up another direction, right? So that's the kind of thing we're doing. We're looking at slope once again. Okay, well, as you'll see, it's pretty important that we use a unit vector in our definition for consistency's sake, but also for what's to come. So this is not a unit vector. So we need to take u, we'll call u our unit vector, but then take v and divide it by its magnitude to get u, right? What's the magnitude of v going to be? The magnitude of v is, I'll bet it's the square root of something. 1 plus 25, 26, root 26 rather. Everybody agree with that? Okay, so my unit vector, I could write my unit vector u as 1 over root 26 times v, right? Which is going to be 1 over 26i plus 5 over root 26i, that is, plus 5 over root 26j. So 1 over root 26i plus 5 over root 26j. Okay, this is our u. Is that clear what I did to find it? That's the direction we're interested in. Of course, it points in the same direction as v, but we need, for a consistent definition of directional derivative, we need to take a unit vector here. Okay, so what? Well, what else does the formula say we need? Go back and look at the formula. It's right here for the directional derivative. What does it say we need? If you're not sure in this section, what do? You take the partials, and you'll get partial credit on the test. Maybe you have no idea how to do the problem, right? But take the partials. Okay. So what was our function? Oh, it was f of xy equals an inverse cosine. All right, you might need some refresher here. Let's say you have y equals the cosine of x, cosine inverse of x. What's y prime or dy dx? Anybody remember? Negative? Very good. Yeah, not a lot of students remember that. Okay, so we'll adjust that formula to work with what we have here, because we have f of xy equals the cosine inverse of x times y. So if you take so f of xy, well, it's just to have it here in front of us is the cosine inverse of x times y. So if you take the derivative with respect to x, now I get a little lazy here and I leave off the of xy, okay? If you're plugging in a point, you better put in what those point values are. If you're plugging in an x and y value, you better put it in what it is. Okay, what's the derivative of f with respect to x at xy? Well, using this formula and adjusting for the fact that we have x times y, what do we get? We get negative, I'll use a 1 for now, 1 over the square root of 1 minus xy, the whole thing squared, right? X squared, y squared. But then, isn't there an inner function? So what's the derivative of the inner function with respect to x? Y. So you can multiply by y out here, or better yet, just make it y on top. I can make that 1 a y pretty easily. Okay? Everybody see how I got that? Okay, what about f sub y? Really, when I say f sub y, I really mean that. I just get lazy about that. What would it be? It's with respect to y this time, so what's going to end up being on top? X divided by the square root of 1 minus x squared, y squared. Is that okay? Let's write down a generic formula for the directional derivative because that's good practice, and then we'll plug in the values of x and y that were given. So the generic formula, the directional derivative in the direction of u, f of x, y. We're going to take f sub x, which is this guy, times, it was u1, right? So if you go back and look at the formula, you take f sub x, evaluated at xy, times u1. Okay, so what's u1? What's u1 here? 1 over root 26. That's u1. And u2 is 5 over root 26. Okay, so that becomes times 1 over root 26 here. Is that what it was? And then plus the partial with respect to y, which was negative x over the square root of 1 minus x squared, y squared, times, I think it was 5 over root 26. Let me make sure I got my negatives in order. Yeah, no negatives. Okay. I mean, of course you can simplify that, but I'm going to leave it like that. Is that okay? And then look, we were asked to evaluate this at a particular value, 1, 0. X equals 1, y equals 0. So what does it become if you do that? So in other words, we're asked to find the directional derivative evaluated at 1, 0. So what does this first guy become? What happens if you stick that 0 in for y? The whole first term becomes 0. Then when you stick the 1 in for x, what do we get? Remembering that y is 0, this term zeroes out, so it's just the square root of 1 on the bottom.
Negative 5 square root of 26.
Negative 5 over the square root of 26. Whoops. So that's your slope of your hill. So you're going downhill apparently. At the point 1, 0, f of 1, 0. If you're standing on the hill at the point 1, 0, f of 1, 0, then I guess if you look in the direction of u, you're going to go downhill because that slope is negative. Does that make sense? Okay. So let's write that down or something to that effect. This is the rate of change of f at the point 1, 0, f of 1, 0 is the z coordinate, right? In the direction of u. I suppose you don't need the z coordinate there. It's still the rate of change at x equals 1, y equals 0, but I'm taking it from the perspective that you're standing on the hill or standing in that region. Sometimes it's not a hill, right? Sometimes it's a depression. The directional derivative gives us these results, and they're very important. So number 1, you could rewrite the directional derivative as a dot product if you so choose. So the directional derivative, if you think about it, if you form a vector out of the partial derivatives, with the first component being the partial with respect to x at xy, and the second component, the partial with respect to y at xy. And if you dot that with u, that's another way to write the directional derivative, isn't it? U being the direction vector. So do you guys believe that, first of all? Yeah, because u has components u1, u2, and if you take this dot product, you get exactly the formula we just had for the directional derivative. Okay? Well, okay, we have a name for this guy, this vector of partial derivatives, and we call that the gradient. So this is called the gradient of f. Notice that f graphs to be a surface in space, right? But the gradient is actually a vector in the xy plane. You can think of it that way. Now, there's some different notation for this. So this is the gradient of f. You might also see del f, or you also call it del f, but it's a kind of this is the most common notation probably, especially in physics. The del symbol, and then f. Okay? All right. So that's what we call the gradient. So note number 2. Okay, so the derivative, the directional derivative, then, as we just said, is del f, using the new notation, the gradient, del f, dotted with u. So I'm just using the new notation, writing the same thing I just had. Del f dotted with u. Does that seem reasonable? Okay, now do you guys remember an alternate form for the dot product? Using magnitude, you could rewrite del f dotted with u as the magnitude of del f times the magnitude of u, which we know to be 1, right? Times the cosine of phi, where phi is the angle between the gradient vector, del f, and the direction vector, u. I'll write that down in a second. But I want to rewrite this right-hand side because we know that the magnitude of u is 1, right? So this formula then becomes just the magnitude of del f times the cosine of phi. So let me write down again where phi is. Phi is the angle between del f and u, the direction vector. Any arguments there? Does that make sense? Any discussion needed? Ask questions if you got them. Okay. So note number 3, which contains a few notes of its own. So note number 3, the properties of the gradient. The properties of del f. In other words, the properties of the gradient. Same thing. And remember what the gradient equals. Now in ij form, okay, in component form, it's basically f sub x comma f sub y, where these guys are evaluated at xy, for generically anyway. Or f sub xi plus f sub yj in ij form, right? The properties of the gradient. Okay. The maximum value. The gradient tells us the maximum value of the directional derivative. The maximum value of the directional derivative is the magnitude of the gradient. Okay, why is that true? Go back and look at the alternate form of it. So this formula with the cosine of the angle between u, the direction vector, and del f. When is this guy at its largest? Because the cosine of phi is always between what two numbers? -1 and 1. Del f, the magnitude of del f times the cosine of phi, is at its largest when the cosine of phi is equal to 1. And that means you just get del f when the cosine of phi is equal to 1. In other words, the largest the cosine of phi can get is 1. So the magnitude of del f times the cosine of phi can get is the magnitude of del f, right? So that's all we're saying in part A of note number 3. Another way to think of that is f increases most rapidly in the direction of del f. Okay, part B. What do you suppose the minimum value of the directional derivative is? What's the smallest the cosine of phi can get? -1. So when the cosine of phi is -1, then the directional derivative becomes negative magnitude del f. So that's the minimum value. The opposite of del f, magnitude del f rather. Okay, so that's saying f decreases most rapidly in the direction of negative del f. F decreases most rapidly in the direction of negative del f. Does that seem reasonable? Okay. Finally, del f in terms of a function, so let me emphasize, del f evaluated at generic inputs x and y is orthogonal. That means 90-degree angle, right? Del f is orthogonal to the level curves of f. So let me show you a picture to convince you that that's true. So remember what the level curves of f might look like. They don't have to be closed curves, but it'll be nice for this picture. So let's draw some level curves that are closed curves. Again, they don't have to be closed curves. A lot of you get the wrong idea. It's only if you set the function value equal to a constant and you get a closed curve would the level curves be a closed curve. Okay. So to stay on a level curve, which means a constant f value, where would you point? What would the direction vector have to look like in comparison with the level curves of f in order to stay at a constant height? Well, I would claim that u would have to be tangent to the level curve. Okay, so this is the type of u, let's say it this way, this type of u keeps f constant. Does that make sense? So if you're moving on a direction or in a direction specified by u and u is tangent with the level curve, that means you're moving in a direction that keeps you at the same height on the hill or in the crevice or whatever the surface looks like. Okay? All right. Now, what's the directional derivative then? So the directional derivative, if f is staying at the same height, what's the rate of change of the function's height with in the direction of u? If the height's staying the same, isn't it 0? Yeah? So, wait a minute. Remember what du of f of xy is. It's del f dotted with u. So if del f dotted with u is 0, then that means you've only got two choices. Either del f points this way, if it's increasing most rapidly in that direction, if the level curves are increasing most rapidly in that direction, or this way, if the peak of the mountain is, say, over here, right? So either del F points that way or that way, which either way it's orthogonal to the level curve and to u, right? I probably would be better said the other way around. Either way, del F is orthogonal to u, which means since u is tangent to the level curve, it's orthogonal to the level curve. That takes some thought, but that picture gets you there. And the fact that u keeps you, if you want to stay on a level curve, then u is going to point in a direction that's tangent to the level curve. Okay? All right. And then I won't prove this, but I will make this statement. Del f of x, y, z. Oh, wait a minute. I just upped it one dimension, right? Del f of x, y, z. Well, if del of f of x, y is normal to the level curves of f, then what do the levels of a 3-input variable function look like? They're not level curves, they are level surfaces. So del of f of x, y, z, when you have a third component, it's a vector in space as opposed to being in the plane. And it is orthogonal to the level surfaces of f. That turns out that the analogy generalizes to higher dimension, in other words. Is orthogonal to the level surfaces of f. And that is a quick way, that it's going to give us a way to find the equation, another way to find the equation of the tangent plane. Let's find the equation of the tangent plane to the surface z squared minus 2x squared minus 2y squared minus 5 equals 0 at the point 1, negative 1, 3. Make sure I copied it down right. I think I did. Okay. Now, you guys already know one formula for finding the equation of a tangent plane. But that formula depends on z being solved, or the equation being solved for z in terms of x and y, right? So here's my idea. We know that if you think of the left-hand side here as a function with 3 input variables, from that last note, we know that del f at 1, negative 1, 3 is going to be perpendicular to f of 1, negative 1, 3. So the function that I'm calling f evaluated at 1, negative 1, 3. And I'll put in the equal 0 to emphasize that we're talking about a surface here. That's a fancy way of saying that that this gradient vector is perpendicular to the surface at the point 1, negative 1, 3. Okay? Well, remember what you need to find the equation of a plane. You need a perpendicular vector, remember that? And a point on the plane. The point on the plane will be the point of tangency. So we're going back basically to the chapter 12 definition or formula for the equation of a plane. Remember, in chapter 12, if the point was x naught, y naught, z naught, and the normal vector was a, b, c, the equation was a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. But now the A becomes f sub x evaluated at x naught, y naught, z naught. The B becomes fy evaluated at the point of tangency, x naught, y naught, z naught. And f sub z is your C. So it's an alternative equation of the plane, and it works every time. The equation of the plane that we gave you last time depends on the fact that you can solve for z, which isn't always possible. Okay. So what are you going to do here? You're going to take the partials, right? If you're not sure about that question in this chapter, just say take the partials, and you'll probably be right. So let's take the partial of f with respect to x, with respect to y, and with respect to z, and evaluate all of those at 1, -1, 3, and that will comprise the components of our normal vector. Okay? So, all right. So let me rewrite the surface down here so we can refer to it easily. Z squared minus 2x squared minus 2y squared minus 5 equals 0. Okay, again, this guy on the left is capital F. So what is f sub x at just x, y, and z? What's the derivative with respect to x? Just -4x. Does everybody see that? Okay. And then what's the derivative of f with respect to y? -4y. And what's the derivative with of f with respect to z? Just 2z. But now let's evaluate these. So what's f sub x evaluated at that point on the surface? That's going to be the point of tangency, that given point 1, -1, 3. So 1, -1, 3. Well, you only have to plug in the x value here, so what do you get? Plug it in right there, you get -4. F sub y evaluated at that point. Plug in -1 for y, and what do you get? 4. F sub z evaluated at that point. Plug so 1, -1, 3. I guess you're plugging in z this time. So what do you get? 6. Okay. So now you're just filling in the equation of the tangent plane. Really the chapter 12 version of the equation of a plane, right? And in this case it happens to be, or doesn't happen to be, it is the tangent plane. Okay, so remember what that is. Okay, you're going to take the normal vector, which is essentially has these components, and take -4 times x minus x naught, which is 1 in this case, plus the y component of the normal vector, which is 4 times what? Y minus a -1, or y plus 1, plus 6, the z component of the normal vector, times z minus 3, I guess, equals 0.